Welcome to the Deep Dive. Today we're tackling a really huge question, maybe one of the biggest philosophical and scientific questions from the last few centuries. Is the universe totally predictable? Or is its future, fundamentally uncertain? For a long time, maybe 200 years, the smartest minds were pretty convinced they knew the answer, and that answer was a definite, yes, everything's already laid out.
Absolutely. And that's where our journey starts, really. Back in the golden age of classical physics, people saw the universe as this perfect clockwork machine. So what we want to do today is trace that whole intellectual story from that peak confidence right through to the mathematical bombshells of chaos theory, which basically showed that long-term prediction. It's fundamentally impossible, even in systems where you know all the rules, perfectly deterministic systems.
And we've got a great symbol for this journey, Laplace's demon. This totally imaginary being, right? Yeah. Dreamed up by Pierre-Simon Laplace way back in 1814. The idea was this demon could know the exact position and the exact momentum of every single atom in the universe all at one single instant.
Right, and if it had that perfect snapshot, plus all the universal laws of physics, well, it could rewind time, see the entire past, and maybe more unsettlingly, it could fast forward and predict the whole future. With absolute, total certainty, no errors. That demon really embodied the height of deterministic thinking.
Okay, so our mission for this deep dive is to figure out what happened. What was the mathematical discovery that showed Laplace's demon was, well, fatally flawed? We're going to trace that collapse from this idea of universal certainty to the kind of terrifying realization of something called the homoclinic tangle, which is basically the moment the math itself had to admit, I don't know.
Now, that confidence back in the 18th century, it wasn't just arrogance, was it? It was built on real success. Newtonian mechanics gave them a framework where determinism wasn't just a nice idea. It seemed to be the actual physical law at work. Exactly. And the core principle sounds almost too simple. A specific cause creates a unique specific effect. That's it. So when you see something that looks random, like flipping a coin, it's not because the outcome could be different. It's because we don't know the starting conditions perfectly. The exact force from your thumb, the air resistance, how it hits the ground, all that stuff. If you knew it all, you'd know the outcome.
Yeah, the sources had some good analogies for that, like an archer shooting an arrow. Its path is totally determined by just a few things, the force, the angle, the wind, maybe. If you know those inputs, you know where the arrow goes. It's a solvable system, predictable.
Or the classic pool table example. Imagine you know the exact position and velocity of every single ball just as the cue ball hits. Theoretically, you could calculate the future movement of every ball until they all stop.
All right, now just scale that thought up, way up. The universe has, something like 10 atoms? Classical physicists basically looked at everything and said, you know what? The whole cosmos is just one enormous, incredibly complex game of pool.
Oh.
I just hope Laplace's demon is better with a cue stick than I am.
Well, their confidence wasn't unfounded. Think about astronomy. They got incredibly good at predicting celestial stuff, eclipses, comets, years ahead of time with amazing accuracy. And that success really bolstered this idea of a clockmaker god, someone who designed this perfect machine, wound it up, and let it run. No need to interfere. Everything was fixed. The future was just calculation waiting to happen.
Okay, but then the first crack appeared.
Right.
It started when they tried to solve something that looked like it should be easy, just a small step up,
Yeah.
the three-body problem.
That's right. The two-body problem, say, just Earth going around the sun, that's neat, it's solvable, elegant math, perfect harmony. But then you add just one more body with gravity, like the moon influencing the Earth-sun system, and suddenly the math becomes, intractable, impossible to solve precisely.
It seems so weird. You figured out the main gravity rules, so adding one more moon or planet, shouldn't that just be like one more step in the calculation? There's that analogy. How do you put an elephant in the fridge? Open the door, put the elephant in, close the door. 3 simple steps. They kind of assumed adding the third body would be just like that. Easy.
Yeah, but it was anything but easy. Now, the big names, Lagrange and Laplace, they did find solutions, but only by using approximations. They managed to show, mathematically, that small disturbances like the moon's tug on Earth wouldn't cause things to fly apart immediately. This was called first-order stability. And this apparent success, proving short-term stability, that's what led Laplace to make that famous statement to Napoleon. I had no need of that hypothesis, meaning the hypothesis of God. The universe looked self-regulating.
Wow, that's some serious confidence.
Yeah.
Especially given what they found out later. They thought they'd nailed eternal stability, but then came these higher order calculations. Horetu did some important work here. And these calculations revealed something called secular terms.
Ah, yes, secular terms. This is really crucial. See, most terms in these complex orbital equations are periodic. They cycle back and forth, like waves or seasons. They balance out over time. But secular terms, they don't cycle. They just grow or shrink, but consistently. Think of it like compound interest adding up over a really long time. Or maybe a ticking time bomb hidden in the math. In the short run, they're tiny, insignificant. But over millions, billions of years, these accumulating errors could suddenly dominate, potentially throwing the whole system's stability into question.
So the perfect stability Laplace claimed was really just short-term stability. The math itself hinted that the system might eventually break down completely because of these accumulating errors.
That's the implication, yes. The long-term picture was suddenly murky again. And this underlying uncertainty, this potential instability, set the scene for a major challenge.
The big math contest.
Exactly. In 1882, King Oscar II of Sweden put up a big prize. He wanted someone to find a single convergent mathematical series, basically. One complete formula that could solve the n-body problem for good, prove the long-term stability of the solar system once and for all. And this is where Henri Poincaré enters the picture.
And Poincaré's approach was different, wasn't it? He realized trying to find the exact number for every atom's position forever was maybe impossible, a dead end.
Precisely. He shifted from seeking a quantitative answer, the exact numbers, to looking for a qualitative one. He decided to study the overall shape, the geometry, the topology of the motion itself.
How do you even visualize that for something like the solar system?
Well, he invented some brilliant tools. First, phase space. Imagine this abstract, high-dimensional space where every single possible state of the whole system, all the positions, and all the momentums combined exists as just one single point. As the system evolves over time, that point moves, tracing out a path, an evolution trajectory through this phase space.
Okay, but for the solar system, that's a space with tons of dimensions, right? How does that help visualization?
It doesn't directly, you're right. No one can picture, say, an 18-dimensional space. So Poincaré came up with another brilliant trick, the Poincaré map, or Poincaré section. Think of it like taking strategic snapshots. If the system is complex but maybe has some underlying repetition, some near periodicity, you don't watch the whole tangled mess of the trajectory. Instead, you only record where the trajectory punches through a specific surface or plane within that phase space. You take a pinprick snapshot each time it crosses. By turning this complex, continuous spaghetti-like motion into a pattern of discrete dots on a lower dimensional surface, maybe just 2D, you can analyze those patterns. Do the dots form neat circles or scatter randomly? That tells you about the underlying stability.
Clever. And initially, using this method, Poincaré thought he'd actually proven the solar system was stable, right? He won the prize.
He did. He submitted this huge, complex manuscript, about 300 pages. The prize committee was all set to publish it. But then, and this is great, a sharp-eyed student, Edvard Fragman, was reviewing it and spotted something, a fundamental flaw in Poincaré's logic about certain types of orbits.
Oh, wow. So his prize-winning paper had a mistake.
Big one. And Poincaré had to scramble, withdraw the paper, fix it. But in correcting that mistake, he stumbled onto something far more profound than stability. He realized that certain trajectories in his phase space, specifically the paths leading towards and away from unstable points, called stable and unstable manifolds, they didn't just get distorted by the third body's influence, they actually intersected.
Intersected. What does that mean in this context?
It means chaos, basically. Once they intersected once, the fundamental mathematics of the system forced them to intersect again and again, infinitely many times. He called this resulting structure the homoclinic tangle.
An infinite tangle, baked into the deterministic laws. That sounds completely paradoxical. How can perfect rules lead to infinite complexity?
That's the mind-bending discovery. The tangle showed this structure had infinite detail, like nested infinities, repeating patterns on smaller and smaller scales. It was so complex. Poincaré famously wrote he even simply did not attempt to draw it. It defied visualization.
Okay, I need to wrap my head around this. This tangle. It's not caused by something random from outside the system. It emerges from the deterministic rules themselves.
Exactly. That's the core paradox of deterministic chaos. And the tangle had a devastating implication for prediction. It proved mathematically that trajectories starting incredibly close to each other, infinitesimally close, would diverge exponentially fast as they moved through this tangled region. So the system is deterministic, the rules are fixed, but because of this infinite sensitivity woven into its structure, the long-term future becomes fundamentally non-integrable. You can't calculate it out indefinitely.
And this isn't just abstract math, right? It has real-world consequences for prediction.
Oh, absolutely. This is where it hits home. Later calculations by people like Jacques Lascar applied this to the actual solar system. They figured out that if you want to predict Mercury's orbit accurately, just 2 million years into the future, which isn't that long, cosmically speaking, your initial measurement of its current position and velocity has to be accurate to within, wait for it, less than 0.38 millimeters.
Less than half a millimeter across the entire solar system, just for Mercury, for only 2 million years.
Precisely. That level of precision is just. It's impossible. Forget knowing the state of 10 atoms like Laplace's demon needed. We can't even know the state of one planet well enough for relatively short-term cosmic predictions. So even if the future is technically determined by the present state, that future is sealed off from us. We can never know the initial state with enough precision. Prediction breaks down.
So the homoclinic tangle is the mathematical proof that Laplace's demon is, well, unemployed.
You could say that. Its job description requires impossible precision.
Okay, so Poincaré discovered this infinitely complex tangle. How did people visualize or understand the mechanism behind it later on?
Right, the how. That came later, significantly with the work of Stephen Smale, an American mathematician. He formalized the underlying dynamic that creates this infinite structure using something called the horseshoe map. Smale showed that the core mechanism creating the tangle's complexity is a repeated process of stretching and folding in phase space. Imagine taking a block of dough, stretching it out to twice its length but half its width, then folding it back on itself like a horseshoe, then do it again, and again, infinitely. Each stretch pulls nearby points exponentially far apart, and each fold brings distant points back together, mixing everything up in an incredibly complex way. That's the engine generating the tangle.
Stretching and folding, creating infinite detail. That sounds a lot like fractals.
Exactly. That's the connection. Benoit Mandelbrot later coined the term fractal to describe these kinds of shapes with infinite detail, self-similarity at different scales. The classic example he used is measuring the coastline of Britain. The closer you look, the more wiggles and bumps you find. If you use a smaller and smaller measuring stick, the total length just keeps increasing, theoretically towards infinity. That infinite self-similar structure Poincaré glimpsed in the homoclinic tangle. That's the mathematical signature of a fractal, generated by these deterministic stretching and folding dynamics.
Okay, so the math was pointing towards this inherent unpredictability for decades. But it didn't really hit the public consciousness until the 1960s, right? With weather.
That's right. Enter Edward Lorenz, a meteorologist at MIT. He was working with a very simplified computer model of weather patterns, just 12 equations. And purely by accident, one day in 1961, he wanted to rerun a simulation. To save time, instead of starting from the very beginning, he typed in the numbers from the middle of a previous run. But he rounded the numbers slightly. He typed in 0.506 instead of the full 0.506127 that the computer had stored internally.
A tiny difference, like less than 1 part in 1,000.
Minuscule. He expected the new run to essentially follow the old one, but when he came back after letting it run for a while, the results were completely different. Wildly divergent weather patterns emerged from that tiny initial rounding error.
And that became known as
the butterfly effect. But we really need to be careful here because the popular idea is a bit misleading. It's not literally about one specific butterfly flapping its wings in Brazil and directly causing a tornado in Texas through a chain reaction.
Okay, so what is it then?
It's Lorenz's discovery writ large. Extreme sensitivity to initial conditions. The butterfly is just a powerful metaphor for an infinitesimally small change. The atmosphere, like the three-body problem, is a chaotic system. To predict the weather accurately, even just say 2 weeks ahead, you'd need to know the initial state of the atmosphere with impossible precision. You'd need data down to the level of every tiny air current, including, yes, the flap of a butterfly's wings, everywhere on Earth, since we can never have that data.
Long-term prediction becomes impossible. The tiny errors in our measurements get amplified exponentially fast.
Exactly. But, and this is the critical point that defines the field of chaos theory, just because the system is unpredictable doesn't mean it's completely random or structureless.
Right, it's deterministic chaos.
Yeah.
The rules are fixed, even if the outcome is sensitive.
Precisely. Lorenz's system, even though trajectories starting close together would diverge exponentially, didn't just fly off randomly into mathematical infinity. The trajectories were still confined. They were constantly drawn towards a specific, complex, but bounded shape in phase space.
The strange attractor.
The strange attractor. In Lorenz's case, it famously looked a bit like a butterfly or a figure-8 mask. The system is chaotic. You never know exactly where on the attractor it will be, but its behavior is still constrained to the specific intricate structure. It has order hidden within the chaos.
Okay, so let's try and pull this all together. It's been quite a journey. We started with Newton and Laplace, seeing the universe as this perfectly predictable clock, easy to understand, maybe even repairable if needed. And we ended up with Poincaré, Lorenz, Smale, watching that clock essentially shatter into these infinite fractal pieces.
Yeah, I think the huge takeaway from chaos theory is this. The universe is governed by deterministic laws, at least at the classical level we've discussed. But as soon as those laws apply to systems with, say, 3 or more interacting parts, which is most of reality, like orbits, weather, fluid dynamics, even biology, the resulting behavior over the long term becomes fundamentally unpredictable. And that unpredictability comes from this infinite sensitivity to the starting conditions, this stretching and folding, this homoclinic tangle baked into the very mathematics.
So the system is determined, but it's unknowable in practice. To any observer, whether it's us or even Laplace's imaginary demon. Like the physicist Sean Carroll said, since the demon doesn't exist, the future might be determined by the present, but nobody actually knows what it is. All we can really tell is the difference between what we can predict and what we can't.
And realizing that perfect determinism can naturally lead to this kind of chaos, it actually highlights the real strength of science. Bertrand Russell had a great quote about this in the source material. He warned against treating scientific theories like religious dogma, saying something like, "I absolutely refuse to sacrifice for my belief because my belief might be wrong."
That's powerful. So the big scientific win wasn't proving everything was predictable, but having the honesty, the readiness to admit error when the math itself, like with the homoclinic tangle, showed the limits of what we can know. Embracing this chaotic aspect of reality isn't a failure. It's actually the start of a deeper understanding, finding this incredible structured beauty like the strange attractor, even within the parts of the universe that are inherently unknowable to us.
Absolutely. And maybe the final thought to leave everyone with is this. If the very structure of systems from planets down to, well, maybe even social interactions makes their long-term outcomes inherently unpredictable due to this extreme sensitivity, what does that imply for our own lives, for our long-term plans or goals? Where might the butterfly effect, that sensitivity to tiny initial nudges, be subtly shaping your own future in ways you can't possibly foresee?